Tonight, let's begin with a quiet question. Not to solve it, but to keep it company. What if the Big Bang was not the first node of everything, but one clear beat in a longer rhythm? What if the future holds another rising pulse, gentle or sudden, that remakes the sky from the inside out? We will move slowly, one idea at a time, and let the possibilities breathe. When most of us hear Big Bang, we imagine a single, unique event, 13.8 billion years ago, when space, time, matter, and energy all arrived together. That picture is not wrong, but it is easy to frame it as a blast in empty space, as if a firework went off somewhere, expanding into an existing room. Modern cosmology encourages a different view. The early universe was a hot, dense, almost uniform state, and what grew was not a cloud inside space, but space itself. In less than a second, the fabric of the cosmos expanded extraordinarily fast, carrying matter and radiation with it. Temperatures were so high that ordinary atoms could not exist. Quarks and gluons moved through a radiant plasma. Only much later did they assemble into protons and neutrons, then atoms, then the first stars and galaxies, and eventually, after a very long time, living beings who could ask where it all came from. So what could a second Big Bang mean? In the calm language of physics, it isn't the universe starting from nothing again, not a complete erasure of time, but rather another universe-scale energy event, intense enough to recreate the extreme conditions of the beginning. It could be a restart after a long contraction, a rebound. It could be a deep change in the vacuum itself that releases stored energy. It could be a meeting of higher dimensional structures that pour heat and light into our world. In each case, the word second does not imply a copy, only a new chapter, perhaps written with slightly different rules. To reach this idea, many theorists begin with a simple discomfort: the singularity problem. If we reverse time in our standard equations and compress the universe back toward its start, the density and temperature climb without limit. We run into a point where the mathematics breaks, and our usual laws stop making sense. Rather than accept that dead end, several modern approaches look for ways around it. Paths that keep the physics finite and the story continuous. If a true singularity is avoided, then the beginning is not an edge but a turning, and a second beginning could be possible too. One family of ideas imagines the universe as cyclical. In that picture, expansion is followed very far in the future by contraction. Galaxies that now drift apart would eventually draw together. Large structures would slowly smooth out under extreme compression, and temperature and density would climb until they resemble the earliest moments once again. At that threshold, instead of a singularity, the cosmos bounces, and expansion begins anew. Each cycle might be separated from the next by spans so long they are difficult to phrase, trillions upon trillions of years. From inside a cycle, the turn would look like an ending. From the wider view, it would be one beat in a long, steady heart. Another line of thought replaces smooth space with something granular at the smallest scales. In loop quantum cosmology, the geometry of space is not infinitely divisible. There is a maximum density, roughly 40% of the Planck density, beyond which gravity's pull is countered by quantum geometric effects. As contraction drives the cosmos toward that limit, the same physics that once drew everything inward can act like a repulsion, preventing a collapse to nothing and turning the fall into a rise. In that view, a second Big Bang is the moment of turning. Not a beginning of time, but a recovery of space from its tightest curve. There are other, equally careful pictures. Some come from theories with extra dimensions, where our observable universe lives on a three-dimensional brain, drifting in a higher dimensional space. If two such brains approach and touch, the encounter can release tremendous energy, heating our brain and starting an expansion that, to us, looks like a Big Bang. In versions of this story, such encounters are not unique. They repeat gently or rhythmically, each time resetting the conditions for stars to form and light to travel, And there is the quieter, more precarious scenario of the false vacuum. The vacuum is not empty. It is a field with properties. If ours is in a long-lived but not absolutely stable state, a rare quantum event in the deep future could nudge it to a more stable configuration. The change would begin as a bubble that grows almost at light speed. Inside that bubble, the constants that shape physics, masses, interaction strengths, perhaps even the pattern of forces could be different. To any observers born there, the opening moments would look like a birth, sudden and brilliant. To us, at the boundary, it would be unannounced and unstoppable. The timescales suggested by current measurements are not near, they stretch far beyond the present age of the universe. Still, as a way to think about another beginning, the idea is precise enough to study. Across these possibilities, one thread stays constant. If there is a second Big Bang, it is unlikely to be a precise replay. The earliest ripples in density could be slightly stronger or weaker. The fundamental numbers might shift by small amounts. The universe that grows might form galaxies differently, or stars with other habits. Some parameters may stay the same, others might move by a breath. The result is not a theatre rerun, but a new performance on a familiar stage. For tonight, it is enough to hold the picture gently. The first Big Bang was not an explosion in a pre-existing room, it was the room growing. A second would be the room being rebuilt from its smallest patterns, whether by a rebound, a meeting, or a change in the vacuum itself. We do not know if it will happen. We do not know how it would feel, but we can follow the ideas slowly and rest with the questions that guide them. In the next part, we will linger longer with the cyclic view, how a universe might contract without tearing, how a bounce avoids an edge to time, and what signs such a past or future might leave in the faint microwave light spread across the sky. For now, let the image settle. Not fireworks, but a quiet heartbeat, somewhere beyond our horizon. When we picture the universe breathing, expanding then contracting, it helps to let go of human timescales. These are not the years that measure a life, nor even the billions that mark cosmic history. They are spans so long that our language can only approximate them. Yet, in theory, the rhythm could exist. A universe that grows, slows, folds inward, and then softly rebounds. Imagine such a contraction. Galaxies that once drifted apart under the pull of dark energy begin, after inconceivable ages, to slow their retreat. The cosmic fabric no longer stretches but settles. Distant stars approach each other across the dark, drawn by the gravity that never stopped calling. The background light, already cooled to almost nothing, begins to warm as density rises. What was once a wide, quiet sea turns once again into a crowded tide. If contraction continued unchecked, the universe would become hotter, denser, smoother, until it reached what the standard Big Bang model calls a singularity. Infinite density, infinite curvature, no space to breathe. But many physicists suspect nature refuses infinities. Instead, as the density grows, quantum rules take over. Space and time themselves would resist further compression. Rather than vanishing, the universe could rebound, an event that, to anyone living inside it, would look like another beginning, another Big Bang. This bounce replaces the end with a curve, a smooth turn in the fabric of existence. In loop quantum cosmology, this turn happens because space-time is not a continuous sheet, but a mesh woven of discrete loops. Like atoms of geometry, these loops set a maximum compactness. When the cosmos nears that limit, gravity stops pulling inward and begins to push outward. The collapse becomes expansion. The darkness becomes light. The universe is born again, but time never truly stopped. It simply reversed its flow for an instant. If this picture is right, our own Big Bang might have been one such bounce. Before it, an earlier universe contracted, heating, brightening, and finally rebounding into ours. The evidence would be faint, subtle, almost erased by 13.8 billion years of unfolding, but perhaps not completely lost. The cosmic microwave background, the afterglow of the first light, might carry tiny irregularities, echoes of structures that once existed before the rebound. Patterns of polarization or a particular distribution of gravitational waves could one day hint at that older phase. To test such ideas, cosmologists look to the sky with extraordinary instruments, satellites that map ancient radiation, detectors that listen for ripples in spacetime. If the bounce left even a whisper, it would be encoded in these faint signals. The work is slow, demanding patience and precision, qualities suited to a universe that measures its life in trillions of years. There are other visions of the cycle, gentler yet grander. In theories involving extra dimensions, our three-dimensional universe might be one brain, floating in a higher dimensional space. Imagine two great invisible membranes drifting toward each other through a wider void. When they collide, the contact releases immense energy. That energy becomes matter, light, and space within the brain, our universe. To us it would appear as a big bang, though in truth it would be the warmth of a meeting between dimensions. After such a collision, the brains could recoil, drift apart, and cool. Then, under gravity, they would slow and return again. Each encounter would spark a new cycle, a rhythm of approach, touch, and separation, repeated endlessly across higher dimensional space. The elegance of this picture lies in its simplicity. It needs no singular beginning. The brains never vanish. They only dance. And their gentle approach before each collision smooths out irregularities, explaining why our universe is so uniform and flat on the larger scales. If the theory is correct, it might even solve some long-standing puzzles. For instance, why is the cosmic microwave background nearly the same temperature in every direction? In this view, the universe had ample time, during the long, slow contraction before each collision, to even out its temperature and density. By the time of impact, the canvas was smooth, ready for a new painting of galaxies and stars. Still, there are questions. How do we test a theory that involves dimensions beyond our perception? What evidence could reach us from an event that occurred before our own time began? Some models predict subtle signatures, weak gravitational waves or delicate asymmetries in cosmic radiation. So far, these hints remain elusive, yet the pursuit continues, driven less by certainty than by curiosity. The quiet desire to understand whether time itself could be a circle rather than a line. To think this way is not to claim that the universe must repeat, only that it might. In this possibility, the cosmos becomes less like a firework, burning once and fading, and more like a heartbeat, steady, vast, and alive in a scale beyond comprehension. In the next part, we will drift deeper into the question of how energy, matter, and entropy behave in these grand cycles, and why the universe's memory of its past may hold the key to whether a second Big Bang can ever truly begin again. If the universe could contract, then rebound, it raises another quieter mystery. What happens to all its disorder along the way? Every star that burns adds to the universe's entropy. The slow drift from order to chaos. Entropy is a measure of how many ways matter and energy can be arranged without changing their overall appearance. It is what tells us why broken glass does not mend itself, and smoke never gathers back into the flame. From the smallest atom to the grandest galaxy, the arrow of time, from past to future, follows the flow of entropy increasing. So if the cosmos truly cycles through death and rebirth, where does all that disorder go? After each aeon of stars and black holes, after every fusion and collapse, could a new, smooth beginning emerge without carrying forward the clutter of the old? Physicists call this the entropy problem of cyclic cosmology, and it is among the hardest to answer, because by the time the universe might begin to contract again, trillions upon trillions of years in the future, it would already be a graveyard. Stars will have burned their last fuel. Black holes will be the final engines of energy, feeding on the ruins of galaxies. Even those will eventually evaporate through Hawking radiation, leaving only faint uniform heat. At that distant time, the cosmos would be almost perfectly still, a thin mist of low-energy photons and elementary particles spread across vast distances. The temperature would be near absolute zero. If contraction began under such conditions, there would be little structure left to create the fireworks of a new birth. Yet somehow, a second Big Bang, if it can occur, would need to start from a low-entropy, highly ordered state like the first one. Roger Penrose, one of the great cosmological thinkers of our era, described this puzzle with elegant precision. He pointed out that the early universe was extraordinarily uniform, far more ordered than seems likely by chance. To produce galaxies later, gravity required tiny fluctuations in density, but overall, the cosmic beginning was smooth. Why? What physical law or condition set that initial order? Penrose offered a thought. Perhaps entropy doesn't survive each cycle intact. Maybe at the moment of collapse or bounce, something fundamental resets. The very definition of order changes. The geometrical degrees of freedom that carry gravitational entropy might dissolve, leaving behind a state clean enough to begin again. It's a poetic idea cloaked in mathematics, suggesting that while matter and energy might not forget, the structure of space-time itself might. Other theorists have proposed different kinds of cosmic cleaning. In some models, the long contraction before a bounce gradually smooths away irregularities, like a lake settling before sunrise. The energy density increases, but the chaos is ironed out by the physics of compression. When the bounce finally occurs, the new expansion starts from near uniformity again. Another possibility, the disorder might be diluted rather than erased. If the universe expands extremely rapidly, as in inflationary models, the entropy could be spread over such an enormous volume that it effectively becomes negligible. To any observer in a new cycle, the cosmos would appear young and orderly, even if the total entropy remains vast. There are more speculative answers too. In theories involving extra dimensions, some physicists imagine that entropy could leak out, bleeding from our three-dimensional universe into higher dimensional space, leaving our own brain refreshed for a new start. In that way, the waste heat of one universe might become invisible energy elsewhere, clearing the stage for the next act. No single idea has yet solved the puzzle completely. The universe, for now, guards its secret of how it keeps time's arrow fresh after so much wear. But the persistence of this question is itself meaningful. It tells us that physics still approaches something deep and unresolved, not only about cycles and bounces, but about time itself. Because if the universe can truly rebound, then the arrow of time, the direction we experience as forward, must somehow reverse, if only for a moment. In that pause, when contraction turns to expansion, what happens to before and after? Does time stop? Does it flip? Or is it continuous, with past and future merely labels for sides of a single curve? Some quantum cosmologists suggest that during a bounce, time as we know it ceases to be meaningful. The equations that describe the universe at those densities are symmetrical. They work the same forward and backward. The distinction between yesterday and tomorrow is an emergent property, not a fundamental one. In that sense, what we call a second Big Bang might not be the next event in time at all, but another region of space-time, like the far side of a mirror, connected by the bounce. Perhaps our universe is just one half of that reflection. For the moment, all this remains theoretical, beautiful mathematics stretched toward an unseen horizon. But the search continues in the quiet language of observation. Scientists look for tiny hints in the cosmic microwave background, in the statistics of galaxies, in the tremors of space-time itself. If we could ever find a trace, even a faint asymmetry or unusual polarization pattern, it might whisper of an earlier universe that once collapsed, bounced, and left its fingerprints on the newborn light of ours. In the next part, we'll travel further into these traces, the relics of old universes that may still shimmer in our sky, and the instruments humans have built to listen for them, not for proof of an ending, but for echoes of a beginning that might happen again. The night sky, to our eyes, seems silent and eternal, But to cosmologists it is a page covered in faint handwriting, letters of light from an ancient time. Every photon that reaches us carries a whisper of what once was. The temperature of space, the direction of its stretch, the small unevennesses that hint at forces we can barely imagine. If there were ever a cycle before ours, a universe that lived, contracted, and rebounded into this one, then the traces of that earlier life might still be faintly visible, preserved in the oldest light of all, the cosmic microwave background, or CMB. The CMB is the soft afterglow of the Big Bang, born when the universe was about 380,000 years old. Before that, the cosmos was too hot and dense for light to travel freely. Matter and radiation were tightly bound together. As it cooled, atoms formed and light was released, spreading across the universe ever since. Today that light fills all of space as a dim microwave glow, nearly uniform in every direction. Yet, if you look closer, it's not perfectly smooth. It carries ripples, temperature variations 1 part in 100,000, tiny fingerprints of the early universe's structure. Some physicists think those ripples might hold more than just our story. They could hold the fading echo of a universe that came before. If the cosmos truly bounces, then information, however distorted, might survive through the turn. Patterns of density, waves in space-time, even the faint shape of old gravitational fields could leave subtle asymmetries in the CMB we see today. The difference would be small, almost lost in the noise, but not beyond hope of detection. This is why modern telescopes and satellites have become instruments of deep listening. The Planck satellite, for instance, mapped the microwave sky with extraordinary precision. What it revealed was stunning. A universe astonishingly uniform yet sprinkled with minute variations. Spots slightly warmer or cooler than average. These variations later grew into galaxies and clusters, into the cosmic web of matter we observe today. But among the known patterns there are anomalies, curious cold regions, strange alignments, that have puzzled researchers for years. Could they be hints, however faint, of something that existed before our expansion began? No one can say for certain. Most of these irregularities have conventional explanations, random fluctuations, instrumental effects, or statistical coincidences. Yet some scientists continue to wonder whether the cold spot or other irregular zones might be footprints left over from an earlier phase of the cosmos. If the universe has cycled many times, perhaps each expansion carries the ghostly memory of the last. Another kind of clue could come not from light, but from gravitational waves, the ripples in space-time predicted by Einstein and detected for the first time in 2015. These waves, moving at the speed of light, are born whenever massive bodies accelerate, merging black holes, collapsing stars, even the universe itself expanding or contracting. If a bounce truly occurred, it would have produced a background of such waves, relic vibrations from the turning of space-time itself. They would be unimaginably faint, but all pervasive, like a cosmic hum beneath everything. Modern detectors such as LIGO, Virgo, and the planned LISA mission in space are gradually improving their sensitivity, inching toward the frequencies where these primordial tremors might still echo. To search for them is to listen for the heartbeat of creation, the soft pulse that might mark the moment one universe became another. These pursuits demand extraordinary patience. The signals are weak, the noise overwhelming. Yet each improvement, each year of data, each new generation of instruments brings us closer to hearing what may lie beneath. Cosmology has always balanced on that quiet edge between certainty and wonder. We measure, we calculate, and in the silence between the numbers, we feel awe. If the bounce model is correct, then our universe may not be unique, and its beginning not absolute. The energy and matter we see, stars, planets, dust, and radiation, might be the latest manifestation of a cosmic pattern that has repeated beyond count. The thought is not frightening. It is strangely peaceful. A cycle implies continuity, a kind of cosmic memory. Perhaps our universe remembers faintly the warmth of its earlier self. Perhaps it carries within it traces of that ancient rhythm, waiting to be recognized by minds patient enough to listen. And if such traces are ever confirmed, if we find the fingerprints of a universe older than our own, it would change not just our understanding of physics, but our sense of time itself. We would no longer live in a universe that began, we would live in one that breathes. In the next part, we will step back from the cosmic background and look at what drives these vast changes, the invisible forces that stretch or contract space-time, dark energy, dark matter, and the hidden geometry of the vacuum that might decide whether the cosmos ends in silence or begins again. When we speak of the universe's destiny, whether it will expand forever, collapse, or begin anew, we are really speaking about a quiet, unseen power, dark energy. It fills the universe invisibly, yet determines how the cosmos moves. We cannot see it, nor touch it, but its fingerprints are written in every distant galaxy. Dark energy is what makes the expansion of the universe accelerate. And in its delicate balance lies the answer to whether there will ever be a second Big Bang. Let's imagine time stretching forward from this moment, not for centuries or millennia, but for unimaginable ages. Stars will fade, galaxies will drift farther apart, and the night sky will grow darker. All of this unfolds under the influence of dark energy. If it continues unchanged, the expansion will never stop. Space will stretch faster and faster until galaxies slip beyond each other's horizons, their light too faint to reach us. Eventually, even the atoms that make us will find themselves isolated in an immense cold void. This future, quiet, endless, and without return, is known as heat death. It is a vision of final stillness, where no energy remains to be used, and the universe fades into darkness. In such a world, there can be no new beginnings, no second explosion of light. But some cosmologists wonder if dark energy is truly constant. What if it changes with time? What if, like a tide, it could one day ebb? In a scenario where dark energy weakens, the expansion would slow. Galaxies now receding might begin to halt in their flight. Eventually gravity, that ancient and patient force, could regain control. The universe might stop expanding and begin to contract. Stars would grow closer again, the background glow warming as everything compresses. After eons of contraction, space would tighten until it reached a limit, and perhaps, at that moment, would rebound. This is one possible path to a second Big Bang, not a sudden catastrophe, but the gentle completion of a cosmic cycle. Expansion, calm, contraction, and renewal, a rhythm too vast for human time yet perfectly consistent with physical law, if the balance of energies allows. There are even wilder variations of this idea. Some researchers propose that dark energy might not simply fade but reverse its sign, turning from a repulsive force into an attractive one. In that case, the acceleration would not merely end, it would flip. The universe would collapse faster and faster, galaxies colliding, stars merging, and all matter compressing into an ever-heating storm of radiation. The density and temperature would soar until quantum gravity intervened to prevent complete destruction, and once again, space could rebound outward. Another scenario, more speculative still, envisions a big rip. If dark energy grows stronger with time instead of weaker, its repulsion could overcome every other force. First, galaxies would break apart, then solar systems, then planets, then atoms themselves. Even space-time would stretch beyond its own cohesion. The universe would not contract or bounce, but dissolve, every distance becoming infinite. After such a dissolution, what remains is unclear. Some physicists speculate that even this extreme expansion might lead to a new kind of beginning, the fragments of one reality serving as the quantum seeds of another. Whichever fate is true all depend on how the vacuum behaves, on the energy woven into the very fabric of nothingness. We live inside this vacuum, though we rarely think about it. Empty space is not truly empty. It seethes with quantum fields fluctuating constantly. In the smallest volumes of space, particles appear and vanish in pairs, a ceaseless hum of virtual life. These quantum fluctuations are what gave the infinite universe its texture, the ripples that grew into galaxies. And they may also decide how it ends. Even in the calmest emptiness, the vacuum's properties are not fixed. They could shift ever so slightly as the cosmos evolves. A microscopic change in the potential of the vacuum field, the energy that fills all space, could cause the entire universe to move toward a new equilibrium. It might collapse into a lower energy state, releasing energy in the process. To us, that release would look like a second Big Bang. It sounds catastrophic, but on cosmic timescales, it would be natural, a kind of quantum renewal of space itself. The universe would not vanish. It would transform. New constants of nature, new rules of physics, perhaps even a new geometry of spacetime could emerge. The laws that govern atoms, light and gravity might shift slightly, and a new story would begin. We cannot predict when, or if, such an event would occur. Theoretical calculation suggests that, if the universe truly sits in a false vacuum, a metastable condition, it could remain that way for an unimaginable time, far beyond any horizon of life or memory. And yet, in physics, metastable never means eternal. Over vast enough time, even the most unlikely transition becomes inevitable. And so, in the silence between equations, a possibility remains. The vacuum could someday tremble, and in that trembling, ignite. A second beginning, born from the stillness of everything that came before, to us. That event would be imperceptible until the very instant it arrived. Faster than light, faster than thought. One moment, the universe as we know it. The next, a new reality blooming outward, filling the void where we once were. For now, the sky's quiet. The expansion continues. The galaxies drift. The stars burn. But somewhere, deep in the language of quantum fields, the script of the next act may already be written, waiting for time itself to turn the page. In the next part, we'll explore how scientists imagine the early moments of any new universe, how inflation, quantum ripples, and geometry sculpt the newborn cosmos, and why those same principles might echo again if another Big Bang ever comes. If another Big Bang were ever to occur, a true renewal of space-time, what would those first moments look like? To imagine them, we can return to what we already know, the first birth of our own universe. In the beginning, there was no place, no direction, no before, only a compact field of energy so dense that every point touched every other. Then, something remarkable happened. Space itself began to expand. This expansion was not steady or gentle, it was sudden and immense. Within a tiny fraction of a second, the universe grew exponentially, an event physicists call inflation. Inflation was proposed in the early 1980s by the physicist Alan Guth, who sought to explain several puzzles in cosmology. Why, for instance, is the universe so smooth on large scales? Why do distant regions share almost the same temperature, even though light could never have travelled between them in the time since the Big Bang? And why does space appear almost perfectly flat, as if the geometry of the cosmos has been ironed flat like silk on an endless table? Inflation offers a simple answer. Before ordinary expansion began, the universe underwent an incredibly brief but violent stretching. During this phase, a field of energy, called the inflaton, dominated everything. Its constant energy density acted like a powerful repulsive force, pushing space to expand exponentially fast, far faster than the speed of light. This didn't break relativity because it wasn't matter moving faster than light. It was space itself expanding. And that expansion smoothed the universe, flattened its curvature, and erased any earlier irregularities. But inflation did more than smooth things out. It planted the seeds of all structure. During that expansion, tiny quantum fluctuations in the inflaton field were stretched to cosmic scales. These fluctuations became the faint density variations in the early universe, ripples that, billions of years later, grew into galaxies, stars, and eventually life. In other words, everything we see today, from the Milky Way to the cell in your body, began as a microscopic tremor in the vacuum. If there were ever a second Big Bang, it might follow a similar pattern. Whether it begins with a bounce, a brain collision, or a vacuum decay, the newborn universe would likely undergo its own inflationary phase. This would again smooth its geometry, erase the remnants of the previous cycle, and spread new quantum ripples that would one day shape its stars and worlds. Inflation, then, may not be unique to our universe. It could be a universal rule, the way every cosmos begins its story. Yet inflation itself raises deep questions. What is the infladon field? Does it truly exist, or is it a mathematical placeholder for something deeper? We have yet to detect the field directly, though many models predict its imprint. Faint patterns of gravitational waves in the cosmic microwave background. Scientists search for these traces, known as B-modes, through experiments in Antarctica, Chile, and even on satellites orbiting Earth. Each year, the sensitivity of these detectors improves, but so far the signature remains elusive, a reminder of how quietly the early universe hides its secrets. And then there is a stranger consequence. If inflation can start once, perhaps it can start again, endlessly. In some versions of the theory, inflation doesn't end everywhere at once. It stops in one region, forming a bubble universe like ours, while continuing elsewhere. Over time, each patch of inflating space buds into new universes, each with its own physical constants and properties. This scenario is known as eternal inflation, and it paints a picture of a multiverse, an infinite sea of expanding bubbles, each a separate cosmos with its own laws of nature. Within this vast ocean of possibilities, a second Big Bang is not an exception. It is the rule. New universes form constantly, like bubbles rising in an endless tide. Ours might simply be one bubble among countless others, its beginning neither first nor last. If this vision is true, then what we call nothing is never truly empty. It is a field forever pregnant with creation, where quantum fluctuations eternally spark new inflations, new spaces, new times. Every so often a new universe blooms, not replacing the old, but joining it in a quiet, endless expansion. This idea stretches imagination, yet it arises naturally from the mathematics of inflation and quantum physics. And while we cannot see beyond our cosmic horizon, we can still ask, if other universes exist, might they ever touch ours? In some models, the boundaries between expanding bubbles can collide. When they do, the impact may leave a faint circular pattern in the cosmic microwave background, a ring of slightly different temperature, a scar from another universe brushing against our own. So far, no clear evidence has been found, but the search continues patiently through the careful eyes of data and time. It may be that the traces are too subtle, or that our cosmic neighbourhood has been quiet for eons. Or perhaps, just perhaps, we are living in the calm between collisions, a moment of serenity in a multiverse that has no beginning and no end. In the next part, we will linger with this idea of the multiverse, not as fantasy, but as a physical possibility born from equations, and explore what it means for meaning itself. If universes are infinite, what does origin truly mean? And can a second Big Bang ever be called new, if creation never really ceased? The idea of a multiverse changes everything, not because it promises adventure, but because it softens the boundaries we once believed absolute. If space can birth more space, if universes can bud from universes, then the word beginning loses its sharp edge. In most models of eternal inflation, new universes appear as bubbles forming in a vast inflating sea. Each bubble begins with its own Big Bang, expands and cools. Inside, physics takes shape, maybe similar to ours, maybe completely different. The constants we treat as unchangeable, the mass of the electron, the strength of gravity, the speed of light, could all vary from bubble to bubble. In one, stars might live only seconds before collapsing. In another, chemistry might never form. In still another, time might flow differently or not at all. And yet, every one of these universes begins the same way, with expansion from a dense, hot state. A beginning that is not the beginning, but a beginning, one among countless others. Our own Big Bang could simply be one note in a cosmic symphony of creation. A second Big Bang, then, would not be a unique event waiting in the far future. It might already be happening elsewhere, right now, silently, invisibly, far beyond the edge of what we can ever see. This picture is breathtaking and unsettling at once. It erases the idea of a singular cosmic story and replaces it with an endless library of universes, some bright, some short-lived, some cold, some still unfolding. And within that library, ours is but one page. But this view also carries a strange kind of comfort. It suggests that creation is not fragile or rare. It is constant, a natural property of reality itself. The multiverse does not diminish us. It situates us within something vaster and more patient than we could have imagined. And yet, even in this infinity, one question remains. Why does this universe, ours, allow for life, for consciousness, for reflection? Among infinite possibilities, why did the constants of nature take values so precisely tuned that stars could form, carbon could exist, and beings could wonder about their own beginnings? Here, scientists turn to what's known as the anthropic principle. It sounds grand, but it is really a statement of perspective. We can only find ourselves in a universe capable of producing observers. If countless universes exist, most may be barren, but we, by necessity, observe one where conditions permit our existence. This principle is not mystical, it is statistical. Just as a fish cannot imagine a desert, conscious beings can only appear in universes where consciousness is possible. From this viewpoint, the fine-tuning of our cosmos is not proof of design or uniqueness, but a quiet inevitability in an infinite landscape. Some physicists find this explanation unsatisfying. It feels like a closing of curiosity rather than its fulfillment. Others accept it as a reminder of humility. In a cosmos that may never end, understanding everything may not be the goal. Perhaps the true purpose of science is not to master infinity, but to keep listening to it. Meanwhile, observation continues. Astronomers search for patterns in the cosmic microwave background that could hint at past collisions between universes, circular traces, faint distortions, or temperature rings too symmetrical to be random. None have been confirmed yet. But every generation of telescopes sharpens our sight. Every decade of data extends our reach. We may never see another universe, but we can feel the possibility pressing softly at the edges of our own. If the multiverse is real, then somewhere, beyond the horizon we can never cross, another bubble may already be blooming. Its first moments might be unfolding right now, its own atoms forming, its own light spreading, its own stars igniting. And perhaps, billions of years from now, creatures there will look into their sky and ask the same quiet question. Was our Big Bang the first? It is a thought both humbling and serene, a reminder that we are part of something that does not stop, something that recreates itself in endless ways. Even if our universe fades, the pattern continues. Energy reshapes itself, space renews itself, and the act of beginning, that spark we call a Big Bang, repeats like a cosmic heartbeat. In the next part, we will turn from infinity back toward ourselves, to the laws that make our universe hospitable, and to the delicate constants that might shift in the next cosmic rebirth. If a second Big Bang ever happens, how different could its universe be from ours? Would physics itself remember the old rules, or start again from silence? Every universe, if the multiverse picture is true, carries its own rulebook. The constants of nature, gravity's strength, the charge of the electron, the speed of light, are the ink that writes reality. But what if, with each cosmic rebirth, that ink is mixed anew? Let's imagine a second Big Bang unfolding in the far future. The dense seed of energy blooms outward again, space inflating, matter forming, light returning. To an observer within, it would look familiar. Galaxies taking shape, stars burning, time flowing. But beneath the surface, the mathematics could be subtly altered. Even the smallest change in the cosmic constants would remake the story of everything. If gravity were just a little stronger, stars might collapse too quickly, never sustaining the balance that allows them to shine for billions of years. If it were weaker, matter might never gather at all. No stars, no planets, only drifting gas and darkness. If the electron was slightly heavier, chemistry itself could break. Atoms might become unstable, molecules impossible. And if the nuclear forces changed even a fraction, the delicate process that creates carbon, the element of life, would fail. Every constant, every ratio is part of a fragile harmony. Our existence rests on a razor's edge, tuned so precisely that even theoretical physicists call it fine-tuning. It's as though the universe knew the melody it wanted to play, and every constant found its note. But in a second Big Bang, those notes might shift. The melody could be rewritten. Perhaps a new universe would form with slightly altered harmonies, one where different elements dominate, where other kinds of stars burn, where life, if it arises, takes forms beyond our imagination, and yet some constants may persist, carried across cycles by deeper symmetries. Just as music can be transposed but still recognized, perhaps the laws of quantum mechanics, the existence of gravity, or the speed at which light defines causality are universal features, the scaffolding of all creation. There's something deeply moving about this idea, that even if everything familiar vanishes, the language of existence may remain. That every universe, however different, still speaks in the grammar of the same cosmic physics. In some cyclic models, these constants are not chosen at random each time, but evolve. Each universe inherits traces from the last, tiny biases encoded in the geometry of its rebound. Over countless cycles, the physical laws could drift slowly, like a river meandering through eons, exploring the landscape of possibility. Our universe, then, could be just one stage in an eternal evolution of reality itself. If this were true, there would be meaning even in impermanence. We would not live in the only universe, but in one link of an infinite chain, each link learning, adjusting, refining. The cosmos would not be a static book, but a poem rewritten forever, its stanzas connected by unseen memory. But how could memory exist between universes? In ordinary physics, the laws of one epoch vanish as the next begins. Everything resets in the fire of creation. And yet, as we saw before, theories like the holographic principle suggest that information, the true essence of memory, can never be destroyed. It may change form, be encoded differently or spread across dimensions, but it persists. If information from one cycle can survive the bounce, even in abstract form, it could influence the constants and conditions of the next. In that sense, every Big Bang could carry a faint echo of its ancestor, a whisper of past geometry, a trace of energy patterns, a subtle imprint that shapes what follows. Perhaps that is why our universe seems so exquisitely tuned, not because it was chosen perfectly the first time, but because it has been learning, cycle after cycle, for eternity. An ancient cosmos practicing itself into harmony. It is a quiet, almost spiritual thought, yet born from physics, not faith. And like much in cosmology, it remains uncertain, unproven, open to wonder. The equations we have cannot yet describe the bridge between one universe and the next, but they point to the possibility that even endings are never final. Some scientists think that if we could decode the faintest irregularities in the cosmic microwave background, perhaps the subtle asymmetry of its polarization or temperature, we might glimpse this hidden memory. Tiny deviations could be fingerprints of universes long gone, smoothed but not erased. To search for such traces is to read the universe as a palimpsest, an old manuscript written over but never fully wiped clean. Beneath its present text, the faint letters of older worlds might still remain, and if one day we find them, we will realize that we're not the first to ask these questions, only the latest consciousness through which the cosmos wonders about itself. In the next part, we'll look more closely at how information might truly survive, through black holes, through quantum geometry, and through the mysterious rule known as the holographic universe, where everything that happens in 3 dimensions may be written on a surface of 2. To understand how one universe might remember another, we have to follow information, the most elusive thing in all of physics. Matter burns, stars die, galaxies dissolve. Yet information, the pattern of what once was, seems to persist. It changes shape, it hides, but it resists oblivion. This idea is more than philosophy. It is a cornerstone of modern physics. It began with black holes. In the 1970s, 2 physicists, Jacob Bekenstein and Stephen Hawking, discovered something astonishing. Black holes have entropy. They are not pure voids, but systems that carry information, and their entropy is proportional not to their volume, but to the area of their event horizon, the invisible boundary beyond which nothing escapes. This simple relation, now called the Bekenstein-Hawking formula, implies that every bit of information swallowed by a black hole is stored on its surface, like a vast cosmic archive written in microscopic code. Later, physicists Gerard 't Hooft and Leonard Susskind expanded this idea into a profound general principle, the holographic principle. They proposed that everything inside a region of space, every atom, every photon, every quantum of energy, could be described by information encoded on its boundary. It's a radical thought. It means that our entire 3-dimensional universe might itself be a kind of hologram, a projection from data written on a distant 2-dimensional surface. If this is true, then information is indestructible. Nothing that ever happens is truly lost. It is only rewritten. The fall of a star, the collapse of a black hole, even the death of a universe, all may leave behind an encoded record on the boundary of space-time. This idea offers an elegant path through one of cosmology's oldest riddles. What happens to information when black holes evaporate? Hawking once believed it vanished forever, violating the laws of quantum mechanics. But in the holographic view, it doesn't disappear. It's preserved in subtle correlations on the black hole's surface. The universe, in its deepest logic, is an information conserver. Now imagine extending this principle beyond individual black holes to the cosmos itself. When a universe contracts, or when space-time bends toward a bounce, the holographic surface that defines it, the cosmic horizon, might carry away its information. That information, encoded in the quantum geometry of spacetime, could then seed the next expansion. In this way, one universe might pass its fingerprints to the next, without transferring a single atom, only patterns, equations, and the memory of structure. Some versions of loop quantum gravity, the theory that treats spacetime as made of discrete quanta, support this notion. At the smallest scales, geometry behaves like a network of finite loops, each loop storing a bit of information about the curvature and energy around it. When the universe collapses to Planck densities, those loops can no longer compress further. They rebound, and in doing so may carry their encoded information into the next cycle. In more poetic terms, the cosmos could be rewriting itself from its own memory. It's not an easy thing to test, but hints might already lie in the data. In the larger scale maps of the cosmic microwave background, physicists search for anomalies, strange alignments, subtle asymmetries, or low-frequency patterns that standard models struggle to explain. Some of these features might, in theory, be remnants of information carried through a bounce. Not messages, not images, but faint mathematical echoes, an ancient fingerprint left in the earliest light. And there's something humbling about that possibility, because it means that every star we see, every atom of our bodies, might be built from patterns inherited from a cosmos that came before. And one day, the information of this universe will seed the next. The cycle is not made of matter or energy, it is made of memory. And the laws of physics are the grammar through which that memory speaks. Even the arrow of time might be part of this story. In a universe where entropy grows, Information disperses but never vanishes. Each era writes over the last, but traces always remain, layered like geological strata. To the cosmos, forgetting is just another way of remembering differently. The holographic principle, then, gives a strange kind of hope. It means that even if the stars fade and galaxies fall silent, the story they told will not vanish into nothingness. It will live on, etched into the fabric of space-time itself. Perhaps, when a second Big Bang unfolds, it will carry those etchings forward, transformed, diffused, and reborn as the subtle laws that will guide the next generation of light. And maybe that is what eternity really means. Not immortality, but continuity, the persistence of pattern through change. In the next part, we'll explore how these patterns could shape the physics of a new cosmos. If information survives the death of a universe, how does it decide the rules of the next? Could the constants, the forces, even the geometry of space arise from the imprints of what once was? If information truly flows from one universe to the next, then the birth of a new cosmos is not a blank page, it is a palimpsest. The old writing is faint but never fully erased. Its structure, its equations, the subtle imprint of its physics, all of it becomes the foundation for what follows. When cosmologists speak of initial conditions, they refer to the ingredients that define a universe's beginning, its curvature, density, composition, and quantum fluctuations. But in a cyclic or rebounding model, those initial conditions are not initial at all. They are inherited. Imagine a vast ocean of quantum geometry, folding and unfolding. When one universe collapses, its information does not vanish into nothing. Instead, it condenses, like dew forming on the surface of a leaf. Then, as the next expansion begins, that dew evaporates back into light and space, shaping the newborn cosmos in ways almost invisible, but decisive. This means that the constants of nature, the forces that sculpt matter, could be outcomes of that inheritance, not fixed eternally, but guided by the lingering memory of what worked before. In this view, the universe is not designed, it evolves. Not in the biological sense, but in a cosmic one. Through countless cycles, it explores the landscape of possibilities, finding configurations that last longer, expand more smoothly, or support greater complexity. Some physicists even call this idea cosmological natural selection. The term was introduced by Lee Smolin, who proposed that universes capable of producing many black holes might, through those black holes, spawn new universes, each with slightly different parameters. In this grand evolutionary process, universes that create more offspring become statistically more common. Over eternity, the multiverse could slowly tune itself, favouring physical laws that generate stability and richness. It's a breathtaking thought, that the very fabric of reality may be self-refining, learning in its own way through the quiet arithmetic of existence. A second Big Bang, then, would not be an accident, but a continuation, another step in an infinite chain of refinement. The shapes of galaxies, the balance of forces, even the emergence of life, all could be echoes of that deep cosmological memory. This idea links physics and meaning in a delicate way. If universes evolve, if laws adapt across cycles, then perhaps the patterns that sustain beauty, structure, and awareness are not fleeting. They reappear, not identically, but as recurring motifs, the universe's way of remembering itself through difference. Some scientists see these reflections in mathematics itself. Equations discovered in one context often resurface in another, as if the laws of nature are variations on an internal theme. From the curvature of space-time to the behavior of subatomic particles, the same symmetries repeat, mirrored across scales. This self-similarity could be more than coincidence. It could be the language of cosmic inheritance encoded through information. But for all its poetry, this notion remains profoundly physical. At the heart of it is entropy, the measure of disorder that marks the passage of time. Entropy always increases, but it never destroys information. It only disperses it. If information is the currency of existence, then entropy is the method by which it is spent, slowly, gracefully across eons. Each universe leaves behind the scattered record of its structure, and those records may serve as the seed for the next. So perhaps the question is not whether there will be a second Big Bang, but what kind it will be. Will it repeat the same laws, preserving familiar constants and patterns? Or will it drift further, exploring new combinations in the infinite field of possibility? If the latter, then creation is not a circle. It is a spiral, expanding outward through time and variation, never truly repeating, but always rhyming. And if information is conserved, then even our thoughts, this very act of wondering about the universe, are not lost. They are part of the cosmic record, woven into the quantum tapestry, infinitesimal yet indestructible. Somewhere deep within the geometry of existence, our curiosity becomes a thread in the universe's own memory. In this way, the universe does not simply observe itself through us, it remembers itself through us. Each consciousness, each moment of awareness, is a reflection of the cosmos looking inward. And when the next universe begins, that capacity for reflection may re-emerge in another form, under another sky. To think this way is to see the cosmos not as machinery, but as continuity. An ancient song with infinite verses, each verse reshaped by the resonance of the last. In the next part, we will explore the final act of this cosmic rhythm. What happens when expansion goes on forever? If dark energy never fades, and there is no bounce, how does the universe end? And could even that silent ending, the long heat death of everything, be a doorway to a new beginning? Let us step into the farthest possible future, not millions, not billions, but trillions of years ahead, where time itself becomes almost abstract. The galaxies that fill our night sky will have drifted so far apart that their light can no longer cross the darkening void. Each cluster will become an island, alone in an ever-stretching sea of space. Stars will die quietly, one by one. Some will collapse into black holes. Others will cool into invisible remnants, spheres of iron and carbon drifting through eternal dusk. This is the long, slow fate of an ever-expanding universe dominated by dark energy, the heat death. At first, the name sounds dramatic, but it describes something tranquil, a cosmic silence. The energy that once drove creation and motion becomes evenly distributed. No more gradients, no more sparks. Without differences in temperature, nothing can happen. No work can be done. No new stars can form. If dark energy truly remains constant, this is how the story unfolds. Space expands forever, faster and faster, pulling matter apart until every atom stands alone. Even black holes, the most enduring structures in the universe, are not eternal. Over unimaginable spans of time, 100 years or more, they will slowly evaporate through Hawking radiation, releasing their stored energy as faint light. When the last black hole dissolves, the cosmos will be a thin mist of low-energy photons, neutrinos, and scattered particles. Everything will be cold, quiet, and uniform, a universe in thermal equilibrium. And yet, even this stillness might not be final. Some physicists suggest that in such a frozen vacuum, quantum fluctuations could still occur, random, spontaneous disturbances in the field of nothingness. Over immense timescales, these fluctuations could briefly form particles, or even entire miniature universes. Most would vanish as quickly as they appear, but once in a while, a fluctuation might expand, igniting a new Big Bang. It would be, quite literally, creation from the calmest possible silence. A spark born not from chaos, but from perfect stillness. This is sometimes called the quantum regeneration scenario. It imagines that even when the universe grows old and empty, it never truly dies. The vacuum itself, the background fabric of space, remains fertile, capable of birthing new space, new energy, and new time. If that is true, then the heat death is not an ending but a pause, the moment before the next breath. And in a poetic sense, it mirrors something deeply familiar. Everything that exists, from galaxies to stars to life, follows a pattern of rise, bloom, decay, and renewal. The universe itself might obey the same law. The mechanism of renewal could differ: a quantum fluctuation, a vacuum decay, a cyclic rebound, or a brain collision. But the essence is the same. The cosmos transforms, not terminates. Some theorists, like Andre Linde, envision this process as eternal inflation, a ceaseless production of new universes budding from an ever-expanding field. Even as our observable cosmos grows old, other regions continue to erupt into being elsewhere. Creation, in this picture, is continuous. Somewhere, right now, a new sky is being born, though we will never see it. It is humbling to imagine that the universe might be infinite not only in space, but also in renewal, that creation is not a rare miracle, but the ground state of existence itself. But there is a gentler way to hold this thought. Instead of thinking of eternity as endless time, we can think of it as completeness, a cycle that holds both stillness and motion, emptiness and creation, a universe that, even in silence, contains the potential for another beginning. Perhaps the heat death is the universe's deep sleep, and every big bang is its awakening. Each awakening carries the memory, faint but real, of all that came before. If so, then there is no ultimate destruction. There is only change of form, matter to energy, energy to information, information to geometry, and geometry back to light. To a human mind, this may feel abstract, distant, almost unreal, but to the cosmos it may be as natural as breathing. When the last star fades, when the final photon stretches beyond sight, the universe will rest, and in that rest perhaps it will dream again, a dream vast enough to ignite a new dawn. In the next part, we'll draw closer to the present once more, to what all these cosmic models mean for us now. If the universe lives, dies, and lives again, what place do we occupy in that rhythm? Are we fleeting sparks, or part of the pattern that ensures the next light will rise? If the universe renews itself again and again, what then is the meaning of now? Where, in this endless cycle of creation and dissolution, do we, small, conscious beings of dust and water, belong? We stand on a planet orbiting an ordinary star in a galaxy among billions. To the cosmos we are brief, almost invisible, yet within us the universe has found a way to look back at itself. The atoms in our bodies were born in ancient stars, forged in furnaces that have long gone dark. The calcium in our bones, the iron in our blood, the carbon that makes us alive, all are echoes of explosions that once lit the young universe. In that sense, the universe has already experienced rebirth many times, not only in the grand cycle of expansion and contraction, but in every star that dies and gives rise to new worlds. The same pattern repeats at every scale. Death feeding creation, chaos giving way to order, order dissolving back into change. We too are part of that pattern. Every thought, every heartbeat, every breath is a continuation of the cosmic rhythm, a tiny reflection of the expansion and contraction of everything that has ever been. When cosmologists speak of entropy, of the slow drift toward disorder, they often sound as though they are describing decay. But entropy also allows complexity to exist. Without it, energy could never flow, and life could never emerge. The same process that ensures the universe's eventual quiet is what allows us to exist at all. It's as though creation and loss are not opposites, but partners, two sides of the same universal movement. To be alive in such a universe is to live in the brief interval between them, the moment of balance when order still forms from chaos, and awareness can bloom in the gap. If there will one day be a second Big Bang, if the cosmos truly resets itself, then everything that exists now becomes part of its prelude. The energy released by our stars, the matter we shape, even the information we generate will eventually join the great reservoir of entropy and information that seeds the next creation. Our lives, fleeting as they are not wasted. They contribute, however minutely, to the universe's memory. Each action, each discovery, each moment of wonder adds another pattern to the cosmic archive, a record that may echo in ways we will never know. We often think of meaning as something we must find or invent, but perhaps meaning is already woven into the structure of reality, in the way it repeats itself, in the persistence of light, in the fact that from silence, creation always returns. The second Big Bang, if it comes, will not erase us, it will transform us. All that we are, matter, energy, information, will dissolve back into the fields that make up spacetime. From there, those fields will stir again. The same fundamental forces, perhaps altered by new conditions, will rebuild the stage for another kind of existence. Maybe there will be no life in the next universe. Maybe there will be more. Maybe consciousness, once awakened, is a pattern the cosmos finds irresistible, one that re-emerges wherever complexity allows. There's a quiet beauty in that thought, that even if we vanish, the capacity for wonder might not. It might arise again under other suns in other beings, who will look into their own night skies and ask the same gentle questions we ask now. What came before? What will come after? Is there an end? Or only transformation? And in that moment when curiosity awakens again, when awareness turns outward and inward at once, the universe will, once more, remember itself. Perhaps that is the true rhythm of eternity. Not endless time, but recurring recognition. A cycle not only of stars but of understanding. So when you look up at the night sky, you're not merely looking back in time, you're looking into the memory of all that has ever been, and perhaps all that will ever be again. In the next part, we will bring this cosmic reflection full circle, returning to the beginning of our journey, the question of the second Big Bang. We'll explore what these theories, from quantum rebounds to holographic memory, tell us about the future and what kind of beginning the universe might still hold. We began this journey with a single question. What if the Big Bang was not the beginning? Now, after wandering through cycles of collapse and rebirth, through black holes, entropy and memory, that question feels less like speculation and more like a quiet possibility. The Big Bang, as most of us imagine it, is a point of origin, a flash of light out of nothing, the birth of space, time, and matter. But modern physics has gently rewritten that image. The more we learn, the less the universe looks like something that began, and the more it looks like something that transforms. Let's trace that transformation, one last time, slowly. When cosmologists rewind the equations of expansion, they do not reach an empty void. They reach a limit, a threshold beyond which known laws fail. It is there, at that invisible border, that new ideas begin. The bounce of loop quantum gravity, the brain collisions of string theory, the slow rebirth of cyclic cosmology, or the random flicker of a vacuum fluctuation. In each of these, the message is the same. What we call a beginning may be the continuation of something older, something that never truly ends. The second Big Bang is not just a future event waiting to happen. It is a principle, a rhythm, a heartbeat of the cosmos. The first Big Bang was not a spark in space, as it was space unfolding. The next one, if it comes, will not erase what came before. It will rewrite it, carrying faint traces of everything that ever existed. Maybe it has already happened many times. Maybe the light we see from distant galaxies is the remnant glow of countless rebirths before ours. Maybe the universe is not a straight line from creation to heat death, but a circle of renewal, where beginnings and endings are only different words for the same turning. Even if we never witness another Big Bang, the idea changes how we see everything. It turns catastrophe into continuity, and loss into transformation. It reminds us that destruction and creation are never separate. They are phases of one ongoing process. In one version of cyclic cosmology, the time between expansions stretches almost endlessly. Each collapse, each bounce, gives the universe a chance to refine itself, smoothing imperfections, redistributing energy, reshaping its constants. That slow repetition could explain why our universe seems so finely balanced. It has been practiced, trained by infinity itself. And in the holographic vision, information never dies. Everything that has ever existed is stored, encoded at the edge of spacetime, waiting to be used again. When the next universe begins, it may carry within it the compressed memory of this one. The pattern of its light, its chemistry, its thoughts. In that sense, even we, fleeting beings of carbon and curiosity, are part of that inheritance. The universe is not just giving rise to us, it is remembering itself through us. Every discovery we make, every question we ask, becomes part of its pattern of knowing. So when the second Big Bang comes, whether through a cosmic bounce, a vacuum decay, or the silent breath of eternal inflation, it will not be the end of our story. It will be our continuation in another form. Our atoms will become the building blocks of new suns. Our information will drift as quantum whispers into the next geometry of space. And perhaps, one day, consciousness will awaken again and wonder, just as we do now. Was this truly the beginning, or just another dawn? There is comfort in this, not because it promises eternity for us, but because it suggests eternity for meaning itself. The universe does not waste. It reuses. It reimagines. It remembers. In the quiet darkness between worlds, between cycles, between the end of one time and the beginning of the next, something waits. Not in space, but as the potential for space. A silence pregnant with geometry. A stillness filled with the memory of light. And when that silence stirs, when the second Big Bang unfolds, it will not sound like an explosion. It will be more like a breath, soft, slow, endless. The same breath that began this universe, the same breath that will one day begin another. In the next and final part, we will bring this long reflection to rest, returning to the place where science meets wonder and where the idea of a second Big Bang becomes not just a theory, but a reminder of how deeply the universe and our own consciousness are intertwined. We have travelled far from the first fire to the final silence, from equations written on chalkboards to the vast quiet of eternity. And somewhere along that journey, the question of the second Big Bang has turned into something deeper. Not when it will happen, but what it means that it could. Science gives us the frameworks, gravity, quantum fields, entropy, geometry, but beneath them lies something simpler, the persistence of creation. The fact that existence, in one form or another, keeps happening. No matter the model, whether cyclic, holographic, inflationary or quantum, all agree on one truth. The universe has a way of continuing. It refuses stillness. Even when energy grows thin and matter dissolves, potential remains. The vacuum still hums. The equations still whisper possibilities. Perhaps this is what we call being. Not permanence, but motion that never quite stops. In the beginning, there was expansion. In the end, there may be expansion again. And in between, there is us, witnesses, brief and aware, living during one of the universe's rare luminous intervals. We are made of the same physics we study. The same entropy that drives stars to burn drives our neurons to fire. The same gravity that holds galaxies together holds our feet to the ground. Every atom in us has been through countless transformations, born in a star, shattered in a supernova, folded into a planet, and, for a while, arranged into the pattern we call human. When we gaze at the stars and wonder about beginnings, the universe is doing something remarkable. It is contemplating its own origin through us. We are the cosmos reflecting on itself. In the quiet style of the sleepy scientist, let us slow here and simply rest in that realization. If there will be a second Big Bang, we will not see it. But we're already part of its cause. Our energy, our motion, our heat, every photon we release, all will one day dissolve into the cosmic background, folded back into the deep fabric that may ignite again. The next universe, in some distant future beyond thought, will be built partly from what we leave behind. That is a kind of immortality physics can offer, not the survival of the self, but the survival of influence. We are participants in a chain of transformations that has no beginning and no final end. And so, the story of the universe is not tragedy or triumph. It is continuity. Each death becomes the condition for the next creation. Each silence carries the echo of future sound. When scientists describe the equations that might govern a second Big Bang, they speak in symbols, metrics, curvatures, and constants. But the essence behind those equations is simple. The universe is not a single event, but a process of remembering how to exist. Maybe every universe is a variation on a theme, the melody of expansion and collapse, of order and entropy, of light and shadow. And maybe this melody plays forever in different keys, on different stages, each one carrying the resonance of the last. If so, then what we call the end is only a change in rhythm. What we call the beginning is simply the next measure of the same song. So, when we imagine a second Big Bang, let's not think of fire and violence. Let's imagine something gentler, a slow rising of light, like dawn after an infinite night. No explosion, no sound, only the soft unfolding of possibility. Space opens, time stirs, energy blooms, and once again from the silence the universe whispers, I am. That whisper is happening now, in every atom, in every heartbeat, in every star burning quietly in the dark. Because in truth, the Big Bang never ended, it only slowed down enough to become us. In the final part we will let the story rest, returning to the first question with fresh eyes. If the universe never truly began, and will never truly end, then what are we looking at when we look up at the night sky? A past event, or a living, breathing eternity? When we look at the night sky, we are not looking at the past. Not entirely. We are looking at something that is still happening. The Big Bang was not a single instant that ended long ago. It was, and still is, the unfolding of space itself. Every second, every heartbeat, the universe continues to expand, carrying galaxies farther apart, stretching the very fabric in which light travels. The afterglow we call the cosmic microwave background is not a relic locked behind glass. It is the faint echo of creation still humming all around us, soft, patient, eternal. So when scientists speak of a second Big Bang, they are not predicting a repetition of what once happened, but acknowledging the universe's tendency to renew itself, to never stop transforming. The cosmos may one day contract, or freeze, or decay, or rebound, but its essence, the drive to become, will remain. Perhaps that is what the universe is, not a collection of things, but a continuity of becoming, a flow of energy, constantly rearranging itself into patterns, galaxies, stars, life, and thought, before returning to silence and beginning again. From that perspective, the universe doesn't need a creator or an ending. It is creation itself, continuous, self-sustaining, infinite in possibility. Even if we can't see beyond this cycle, we can feel it, in the pulse of our blood, in the burning of a star billions of light years away, in the quiet certainty that the same laws governing distant galaxies are the ones that let us breathe here and now. We are, each of us, made of that same expansion. The hydrogen that fuels the stars also fuels our hearts. The light that began 13.8 billion years ago has never truly stopped. It simply changed form, slowed down, cooled, entered matter, and eventually became consciousness, asking, where did I come from? Maybe that is the most beautiful symmetry of all, that the universe's question became us. And if there will be a second Big Bang somewhere beyond the horizon of time, it may not feel different from this moment. A quiet stirring, a pulse of light returning to being, an old memory rewriting itself as something new. We may not be there to see it, but perhaps, in some quiet way, we already are, because everything that ever existed, every photon, every atom, every thought, will take part in it. When the next dawn comes, When space awakens once more, the light that shines will not be new. It will be the same light, endlessly transformed, endlessly reborn. The same light that began this universe. The same light that burns now in our stars, in our eyes, in our questions. And so the story closes, not with an ending, but with a breath. A universe exhaling one world, inhaling the next, forever beginning, forever remembering. Somewhere, far beyond the boundaries of time, another sky will open. Another observer will look upward and wonder, was there a first Big Bang, or a second? Or have they always been one and the same, and the universe, vast, silent, eternal, will whisper back, there was never one. There was always only me. Thank you for listening.